Swayam Prabha. Digital India. Educated India.
In this lecture, let us begin discussion about basics of kinetic theory of gases. We will begin with significance of revisiting basics of kinetic theory of gases in a study of hypersonic flow. And then we will move on to discuss a number of concepts. Not all of this should be new to you. It would be more of a recapitulation, but some new facts may be there here and there. So, we will look at particle velocity, particle collisions and specular reflection after collision from a boundary, pressure that is felt by a boundary of say a vessel within which the particle is confined due to the particle collisions which occur on the vessel walls, particle translational velocity, etc. And we also talk about particle translational energy. So, we can just add on to what we have written here. We would also like to look at the energy aspects. We begin with the questions that are basically addressed in a discussion of kinetic theory of gases. So, let us assume that we are studying a single species gas which is confined within a box, and we would be interested to know how frequently a particle, which may be an atom or a molecule, collides with the neighboring particles as well as with the walls of the box. In the process, how many collisions per second on an average would occur when the particle moves through these large number of particles or moves across the particles and reaches the wall and so on. So, every particle that we look at, it has to encounter a large number of collisions per second on an average. So, we need that average measure. What distance does a gas particle move before it collides with another particle? That is another question to answer. And what is the average velocity or speed of a particle? Not that all particles will have the same values, there would be a distribution, but then we also need to know some kind of a population distribution in terms of the velocity and speed distribution of the particles which comprise the thermodynamic system. So, the next question we would be interested to raise is, why are we interested in this information? So, the issue is that we have learned about the different atomic and molecular energy modes in week 6, which we just recapitulated again in the previous lecture of week 7. When the gas particles collide, energy transfer takes place between different energy modes, and there may be energy mode, there may be energy exchanges across modes, which is an interesting part. And we already know several times we have learnt about it and recapitulated that there are different modes that have to be thought about: translational, rotational, vibrational, electronic. So, we have to be concerned about all the modes of energy that we are dealing with. Then the other issue is chemical reactions would also occur as the particles collide more often and more in a more agitated manner. If they collide, there are increasing chances of chemical reactions happening. Collisions between the gas particles would take time to occur, which is again a very important point, which is the last bullet point here. This is a very important issue. That means, we cannot expect all the things to happen instantaneously. We have to allow time to the particles to collide and then bring about the changes. So, one of the changes that they bring about is energy transfer between different energy modes, and the other important change that they bring about is the chemical reactions which they initiate. and all that takes time to happen. Therefore, the consequences that occur due to particle collisions need sufficient number of collisions, and sufficient number of collisions would mean enough time for the collisions to happen. The collisions may be happening at a very rapid rate, but that does not mean that it will happen instantaneously. The energy transfer and chemical reactions would not occur before a sufficient number of collisions. Let us see the issues in the next slide. Why are we interested to study the particle collisions? So, if this is the question, how do we go about answering it? And the other question that is waiting for us is, how does it help our study of hypersonic flows? So, we are not just looking at the particle collisions for an academic interest, but we have a distinct application in mind, that it is connected with hypersonic flows. So, we need to understand what is the relevance. Going back to that box that we had earlier talked about, let us say that the gas is stagnant and it is located within the box. So, not that the particles are exactly stagnant, but they may be moving around within the box, and therefore, in a bulk sense the gas is stagnant within the box. That is what it means from a macroscopy point of view. Therefore, it is not flowing, for example, into a hypersonic wind tunnel, or it is not flowing over a hypersonic vehicle during atmospheric entry, or it is not flowing at a very large velocity into a rocket engine leading to the combustion, etc. So, if it is just confined and stagnant in a macroscopic sense, then if we allow sufficient time and we wait for the required number of particle collisions, those collisions will occur in the gas, and once they have occurred, after that time period the gas will be at equilibrium. It will attain the equilibrium thermodynamic and chemical properties. So, this is something that we had discussed in the week 5 contents. So, we by now know how to go about doing the equilibrium calculations. On the other hand, if the gas is rapidly flowing and let us say the conditions are hypersonic, so you know that the typical velocities associated with such flows are enormous. Whether it is a flow through a wind tunnel, or it is over a hypersonic vehicle, or it is through a rocket engine, or any other hypersonic situation, the fluid elements move extremely fast through the geometries of interest, and the gas particles are carried far downstream of the important entity that we are looking at, much before the necessary number of particle collisions can occur to take them to an equilibrium condition. Therefore, there comes the situation of non-equilibrium. They have not gone the essential number of collisions to bring them to an equilibrium state, and therefore, now they are in a state of non-equilibrium. To deal with non-equilibrium flows like what we have mentioned now, we have to deal with the frequency of the particle collisions. That is where it comes in, and therefore, the rates at which those are happening come in. Another effect of the non-equilibrium is that the transport properties of the gas would get modified. So, what are the properties we are talking about? The viscosity coefficient, the thermal conductivity, the diffusion associated with momentum, heat and mass exchanges, those properties get altered. These properties are affected by the mean distance a particle moves between one collision and the next, which we state as the mean free path. So, on one hand, we have to be aware of the frequency at which the particle collisions are happening. On the other hand, we have to be aware how far does a particle move before it collides with another, which gives the concept of mean free path. We now understand how these parameters are of enormous importance if we are looking at non-equilibrium situations. If we have not allowed the gas enough time to remain in equilibrium and we have hurried through the process, then we encounter this difficulty, and then we have to account for these effects, without which our calculations will go wrong. Keeping all this in mind, let us relook at what we are focusing at in week 7. We will continue with the microscopic picture of the of the thermodynamic system, that it is comprised of a large number of particles, and that is the picture we had taken in week 6. We are extending it in week 7, and we will narrow our attention to just the rapid translational motion of those particles as far as the kinetic theory content of the course is concerned. We will see that some important characteristics of gases are dominated by this translational motion. And in week 5, we learned how to calculate the equilibrium thermodynamic properties and chemical composition of a chemically reacting mixture, while in the week 7, in this week, we shall extend our learning. We will calculate the non-equilibrium thermodynamic properties and chemical composition of a chemically reacting mixture. Therefore, here, as you have now got a clue that we have to definitely deal with rates. Beginning the discussion on that box that we were talking about a few minutes back, here within the box we are confining our attention to one particular gas particle which has 3 components of velocity in Cartesian space. We are marking a few faces of that box, the front face, the right face, the top face, and incidentally it is a cubical box with edge lengths of L along the x, y and z axis respectively, and they have been indicated as x1, x2, x3. It's as good as saying that these stand for x, y and z. And then vectorially you can show the instantaneous velocity of the particle as the c vector comprising of cxi, cyj plus czk, all the unit vectors with hat on top. And let the c vector be the velocity of the gas particle before it collides with the wall of the box, and c2 be the velocity after collision. So, here we are talking about the particle moving towards the wall and getting reflected. Now, the above figure, it shows a single gas particle which is being tracked, while there are a very large number of gas particles which are actually existing within the thermodynamic system within the box, but we are confining to our attention to a single particle for the time being, and we are as though keeping all the other gas particles invisible. Having said that, we assume that the tracking happens over a very short time interval during which the particle does not collide with any other gas particle, but it collides with the wall of the container. Now, when the gas particle reaches the wall, it of course reflects back. The reflection of the particle happens specularly. Now, what does that mean? We will just put some equations together which will probably give you a clearer feeling. Let us say this is the particle velocity before collision and c2 is after, as we have already mentioned. Now, we have written it down vectorially. Now, specular reflection has its own requirements. The first thing is that the mod c and mod c1 and the mod c2, that means the magnitudes of the vectors c1 and c2 both before and after collision, they need to equate, which means the lengths of the arrows indicating those velocities have to be equal. And remember that this specular reflection happens only if the particle is reflecting from the wall in an elastic sense. Notice that before it hit the wall, it has a velocity of x1, cx1. After reflection, the cx2 becomes minus of cx1. So, that is one change. The other thing is, along the y direction, it had cy1 which is conserved. We are not seeing the cz1 and cz2 because we have just taken a projection in the xy plane as we observe the particle in this figure. So, the cz1 and cz2 are not visible, they would be into the plane or out of the plane and they would remain conserved. So, this is basically the configuration of specular reflection of a particle from a wall which is normal to the x axis. Similarly, there would be other walls of the box which may be normal to the y axis or z axis, and now you know the rules of the game, what we mean by the specular reflection. Now, if you note the momentum of the particle as it approaches the wall, before it collides with the wall, its momentum is given by its own mass, the particle mass, into its velocity, which is the Cx. Since we are talking about its movement along the x direction, which will help it to reach that wall, we are just looking at that component of the momentum. Cx incidentally is nothing but Cx1, and after the reflection or the collision, it becomes minus Cx because the vector changes its direction, and minus Cx is nothing but Cx2, while Cx was Cx1. Therefore, due to the collision, there is a momentum change along the x direction. Now, we just consider the magnitude, not the sign as well, and that gives us the momentum change. It is 2 times the mass into the velocity of either approach or retreat. Now, as the particle traverses the x direction with velocity magnitude Cx on an average, it would perform the following number of complete to and fro traverses of the box length L along x in unit time. So, what we mean to say is that along the x direction, the box has length L and the particle is moving to and fro towards the right or towards the left and having a large number of collisions over every unit time. We are trying to do the calculations in that regard here to find the number of complete to and fro traverses in unit time, and that of course depends on 2 things. One is the total length that you traverse during a to and fro, which will be 2L, and the velocity at which you do it, based on which every to and fro motion will involve a small time delta t, and if you take a reciprocal of that, you end up getting the number of complete to and fro traverses. That means those are the number of collisions or impacts that it makes on the face of the box. Therefore, the time rate of change of momentum of the particle when impacting the right face will be momentum change per collision into the number of collisions per unit time. So, now comes the number of collisions in addition to the momentum change per collision, and that gives you the time rate of change of momentum of the particle for all the impacts that it makes in unit time. Now, as it is undergoing this momentum change, from second law of Newton, we know that it would involve a force generation on the right face of the box. Similarly, because it is impacting the left face as well, the same kind of momentum change happens with respect to the left face of the box. So, if the right face faces a pressure due to these collisions, same would be the situation for the left face. How do we compute the pressure? Since we have now got the force from the time rate of change of momentum, we have already worked out the expression here, we put it here, and then we divide it by the area being the area of that particular face of the box. All the box faces incidentally are going to have the same area, because it is after all a cube, and therefore, the calculations take place and you get to an expression for pressure, which is m c x square by v, v being the volume of the box, which is given by L cube. We have been discussing about only one particle colliding with the right wall. Since a large number of particles are there in the box which remained invisible, we decided to do that for our own convenience. However, we cannot keep away from that discussion for too long. We have to account for their effect too. So, when they collide with the right wall, there are going to be a large number of collisions because of the large number of particles. They have their own masses, they travel with their own velocities, and therefore, there would be a pressure which will develop as a consequence of all the impacts which are made. So, if there are I number of particles, for example, you would have to sum it up in this manner, taking their individual masses and square of their velocities. And by virtue of their movement between the right wall and left wall, they are also colliding with the left wall as frequently as the right wall, and hence an equal pressure is felt on the left wall, which was already mentioned. In a similar manner, remember that the pressure is exerted on the front and rear faces as well as the top and rear faces of the box. So, when it comes to front and rear faces, if you go back to that sketch which we left behind, you will find that the pressure is given by an expression involving C I y square, while for the top and bottom walls you will end up getting an expression involving CIZ square. When you add these three equations, the three equations involving pressure acting on pairs of walls, then we get a measure of the average pressure felt on the walls of the box due to particle collision. So, you get a 3p when you sum up, and then all the square of velocity components get involved. Essentially, that gives rise to the square of Ci, and the 3 over here goes over to the denominator on the right hand side, and we get an expression for average pressure that is felt inside the box or on the walls of the box, where Ci is the magnitude of the velocity of the ith particle. Now, from the above equation, we can write the following facts, let us say. So, the total kinetic energy of the system of I particles by virtue of their translational motion can then be written in this form. Since we are only taking translation of the particles, therefore, we have to specify this is basically the kinetic energy purely due to translational motion. And combining the P equation and E dash trans equation, we get PV into PV is equal to 2/3 E dash translational. So, this is the kinetic theory equivalent of the perfect gas equation of state. So, earlier we have discussed about perfect gas equation of state, which was derived from the classical thermodynamics, and then we talked about perfect gas equation of state, which can be derived from the statistical thermodynamics point of view, and now we come up with the kinetic theory equivalent of the perfect gas equation of state. Of course, in classical thermodynamics, we remember that it was postulated basically, not that it was derived from first principles, it was postulated from experimental data generated by some of the most well known scientists of all times, while in statistical thermodynamics we could derive it from first principles. Similar things happen for kinetic theory. Now, this equation is applicable when calculations are done on unit mass basis, keep that in mind. When the calculation has to be done on per mole basis, then you have to involve the molar volume and the kinetic energy per mole, in which case we take away the dash from the expression for the energy in the translational motion, and the equation now looks like this, which is modified with respect to the earlier form, which was on mass basis. You should keep track of all these equations individually and use them as is required. Since equation of state on mole basis was written like the way we just saw in the previous slide, towards the bottom of the previous slide, we are able to write it like this when we compare it with the finding of the kinetic theory, because in kinetic theory we came up with the P V, where the V is the molar volume, to be 2/3 of the E translational. The perfect gas equation of state on a molar basis is known to be P molar volume into universal is equal to universal gas constant into T. Therefore, comparing the two forms, we can come to the conclusion that E translational is nothing but 3/2 into the universal gas constant times the absolute temperature. So, this is the same result as obtained from statistical thermodynamics, if you remember. Only thing is, I leave a small work for you to show that the small e translational, which was expressed as 3/2 into specific gas constant into the temperature, is equivalent to the finding that we have over here. Now, that of course was derived using partition function approach in statistical thermodynamics. Here we are using purely kinetic theory approach to come to a conclusion like this. Since in kinetic theory we are dealing with particles, we would like to obtain the expression for translational energy on per particle basis also, in which case you have to involve Avogadro's number and you have to do an operation like this where you divide E translational by Na, and therefore you end up getting the universal gas constant divided by Na, which takes us to the Boltzmann constant here. So, the mean kinetic energy of a particle then would come out to be 3 by 2 k times T. Thus, temperature is a direct measure or index of measure of mean kinetic energy of a particle in a system, because we have clearly shown that E translational or the epsilon translational, which is the per particle measure, both of them are proportional to the absolute temperature. Also, we notice that PV is basically a measure of energy, which was adequately demonstrated through this form, either this form or this form. So, important facts are unfolding here, which you should be taking track of. We return to the equation for average pressure, and it is divided by the total mass of the system. If you do so, then you create a volume by mass over here, the inverse of which will be density, which comes up later on. And then here the mass is basically coming from a summation of the mi's over all the particles, and from the above equation we derive the definition for the mean square velocity, which is a very important concept. So, it is indicated as c square bar, and that is given by this, and because the m by v is rho, you can further write this equation in a form like this: p by rho is equal to 1/3 of mean square velocity, or p equal to rho by 3 into mean square velocity. Again, the perfect gas equation of state can be written in this form: p equal to rho RT, we know from our prior knowledge, and therefore the mean square velocity is given by 3 RT. So, this is again another very important result. The root mean square velocity of particles is given by this equation, and revisiting the E translational equation, which is the mean kinetic energy of a particle, we recall about this. Since E translational is directly proportional to T, higher the value of T, higher is the mean particle kinetic energy, and vice versa, which is clearly evident from this equation. It is independent of the mass of the particle, because if you just look at this form, you do not see the evidence of Mi really very explicitly. All particles residing at the same temperature carry the same translational energy. It is evident from this form, and the Ci is given by under root 3 kT by Mi, which tells us that at a given temperature T, the heavy particles will on an average move more slowly than the lighter particles, because the heavier particles will have a larger Mi, correspondingly a smaller Ci, and vice versa. And that clearly indicates about a velocity distribution based on the mass distribution of the particles which constitute the system. And then comes the concepts of what happens when the particles are colliding with each other. So, if you look at a molecule which we name as M1 here, and it is close to another molecule which we call as N1, which is about to collide with the molecule M1, we often call them as billiard ball models, where each one of the molecules have some sphere of influence, and when they are moving close enough to each other, they cannot penetrate that sphere of influence basically, and therefore it basically boils down to showing the effect like this, where they maintain a distance of d between their centers at the minimum. The radius of influence of a molecule is indicated by that distance d. Any colliding molecule whose center comes within a distance of d of the given molecule is going to cause collision. So, this is basically the definition of collision of molecules following this billiard ball model, and this basically gives an idea how the molecules interact in this kind of situations. The molecules move through the medium carrying along with them this sphere of influence, and let the molecule be translating at the c bar velocity. The actual path that it follows is going to contain the collisions that the molecule has with neighboring particles, and it may so happen that if you are following the molecule M1 starting from some time t equal to 0, the location at which it encounters the first collision after t equal to 0 may be this, where it changes course, then moves on, faces another collision at the second location, and so on. So, the typical path may look like what we have over here, which we are indicating as an actual path followed by the molecule, but we often hypothesize it and we define an imaginary path which shows the molecule translating with the c vector without collisions. It is as though it maintains its magnitude and direction without the effect of collisions. So, if it is encountering collisions, then the mod c bar is constant, but the direction keeps changing, which happens after each collision, while in the hypothetical path or the imaginary path, it continues to move along the same straight line it was following right from the beginning, irrespective of the collisions it actually encounters, maintaining the c vector both in terms of direction and magnitude. Here the dots have been indicated just to keep in mind that it actually encountered collisions, where those are the points where the neighboring molecule came closest to this particular molecule, causing collision. There are other important concepts which we will catch up in the upcoming lecture. They involve the volume that the molecule sweeps by virtue of the influence that it carries along with it, and then the collision frequency that it has based on its collision cross section. These concepts along with mean free path are going to be taken up in the next lecture. So, let us sum up and conclude saying that in this lecture we started our discussion with the significance of revisiting basics of kinetic theory of gases in the context of a study of hypersonic flow. So, we tried to justify why this study is important for us. Then we studied various aspects of gas particle motion. This includes particle velocity, particle collisions, specular reflection after collision, particle translational energy, and so on. The discussions on this lecture would be followed up by some more concepts which would be discussed in the next lecture. Thank you.